So someone asked a question and I promised to iterate and answer the question properly. So last time I talked about during acquisition, there's what we call the split spread and single-ended spread for acquisition, where the split spread means the source point or short points, the source is in between the receivers, and the single-ended spread where the source is at the end of the receiver line, and this is usually common for marine acquisition. And for the split end is common for land acquisition. Then I try to explain also concept of the spread configuration and orientation, where I told you that your receiver lines has to go perpendicular to your strike line, especially if you want to image your fault. So you have to cut across your structure, across the strike line. So you go perpendicular to the strike line thereof, or to an angle to the strike line. So your receiver lines are not going to go in line with the strike line, so that when you look at your seismic data in the receiver in the inline direction, you see your fault plane, the outline of your fault plane. Okay. I also talked about receiver spacing, receiver lines, and short line, and also short interval, receiver interval, and also SWATs. Okay. Is there any confusion so far? Any questions? So in the absence of any, can somebody tell me what a SWAT is? Can somebody try to explain to me what a SWAT is? When you say SWAT, the seismic acquisition, what it means?
Okay, sir, let me try, sir. I want to
Yeah,
try.
go ahead. Yeah, go ahead.
So I will just say it's just a term that is used to describe overlapping of receivers and source lines.
Okay. Not exactly that. Okay. What else? Any other attempt?
What is SWAT?
What's a SWAT? Any idea? I'd like somebody to just tell me.
Can you hear me? Can anybody hear me?
Yeah, I'm hearing you.
Okay, SWAT is like a small unit of data acquired from a whole area.
Okay. Yeah, that's correct. A smaller unit of the whole acquisition area. That's a SWAT. So if you have let's say you have an oil block this big, okay, and the oil block is like maybe 70 kilometers by maybe 50 kilometers, something like that. So you know that it means that this place will be about 3,500 square kilometers, the whole block. Okay? The whole block will be like 3,500 square kilometers in size. So this block will be your OML. It could be any OML, maybe OML 10 or whatever. So I don't know. So if you want to acquire seismic data, your receiver lines are going to be, let's say you want to run your receiver lines in this direction. You're not going to, most times the lines are not that long to cover the 50 kilometers. So you're not going to have a receiver line that will likely run from the beginning here to the end here. So you will not most times not have a receiver line this long, covering 50 kilometers, because the longer the line, the more complex it is to manage the receiver line in terms of physical. When I mean managing, physical management in terms of maybe you to avoid having line issues along, maybe the line getting cut along the line or vandalized and all that. So it's a long distance running it. So most times they share it into smaller lines. So you can have the receiver lines running this way. Okay, just covering this portion of the block. Okay, so depending on the number of lines. So this first one is quite too long, so it's out. So what happens is that you now shoot in this place. You now shoot your receiver short lines perpendicular to the receiver lines. Okay, so when you do this, you have finished this area. So just as the person, someone answered, so a small portion of this block has been covered. So this small portion that has been covered will become your SWAT 1. So this area will be termed SWAT 1. Okay, so this is your SWAT 1. So the acquisition team will extend their receiver lines. Okay, and let me get another pen. So the acquisition team will extend their receiver lines and continue acquiring in this side. Okay, so what they do is that they will overlap. So the last receiver line on SWAT 1 might become the first receiver line on SWAT 2. Okay, and so that's where the overlap you mentioned comes in, Kudus. So you have your overlap and then the second SWAT. And then they also shoot on that SWAT. So the second SWAT will now be termed, let me use another color. This will become your SWAT 2. This area becomes SWAT 2. Okay. And then so on and so forth. They continue the acquisition into SWAT 3 and all that. So they keep dividing the field into small units in order to be able to cover it. This small unit, this length might be up to 20 kilometers in length. And you know, the whole length of the area is about 50 kilometers and maybe by 70 kilometers. So you're just dividing it into small blocks, like the way you do your tiling in your house. You can't tile the whole room with one big sheet of tiling material. So you divide it into small blocks of pieces of tiles. So that's exactly what swatting does. So you have this yellow one, SWAT 1, blue one, SWAT 2, purple SWAT 3, and so on and so forth, until the whole block of 3,500 square kilometers is covered. So that's what basically happens in swatting. So when you hear SWAT, that's what it means. But during our processing, the whole data will also now be gathered as one. Okay, so the whole block will produce a volume of the whole block, even though you acquire them in small bits. By the time they are doing processing, you do what we call merging. You merge all the SWATs together and they become one big volume of the subsurface. So that's basically what this slide is talking about. Then I explained the common midpoint and common depth point. They are basically the same things. Common midpoint referencing the center between the midpoint or center between the receiver and the shot on the surface, and also that same midpoint in the subsurface becomes your common depth point. Okay, so this cartoon shows them in 2 dimensions and then also in 3 dimensions. Then I try to explain to you what a natural bin is. Also here, we have the binning is during your processing, you need to reference your data into bins in order to make it easy, because in the subsurface, you have your midpoints or your CDPs. So your CDP gathers have to be within a bin, okay? So what you do is that you use the distance between your individual receiver, okay? So your receiver spacing, okay, and your short spacing, is what is used. So, okay, the receiver spacing divided by 2, multiplied by the source spacing divided by 2, that gives you your natural bin, and this place is what the natural bin is. So within your acquisition area, the bin is calculated using the size of the receiver spacing and the short spacing. Sometimes you can also even rebin it and make the bin point natural bin sizes to be smaller. So what the idea is that within the bin, the dots here in the center of the bin represents what common midpoint. Okay, it represents common midpoint within your acquisition area. Next is your fold. So within a bin, you will have several midpoints, okay, that are corresponding to different receivers and different sources. So for instance, on the cartoon on the left, you can see we have a midpoint here on this bin, okay. Let me get a yellow marker. So we have this bin, and in the bin, in the center of the bin, we have several midpoints, and there are about 5 of them. So between this receiver here on the far left and the short on the far right, this bin becomes a midpoint for both of them. And also between this receiver on the source on the upper part of the display and the lower part, the receiver on the lower part, the same point becomes their midpoint because it's at the center of them all. And so the more you have receiver points and the source points that are using the same bin as their CMP, that gives you the number of folds. So if you have 5 receivers imaging this particular common midpoint, it means that the data is a 5-fold data. So this is also what this other cartoon on the right is trying to illustrate, that this bin within the center of the bin is a CMP to 5 different receivers and 5 different shorts. And each of the different receivers will generate a trace. And these traces will definitely give information about the subsurface where these midpoints or common depth points are occurring. So that is what fold is all about. So the number of receivers that image a particular spot or a particular CMP or in the subsurface, CDP rather, in the subsurface is the number of fold of that data. So somebody asked me to throw light on fold, and I think that's that. So I added a few more slides to elaborate that. So on this cartoon, still on fold, let's assume you see the yellow spot in our data, this yellow spot somewhere in the subsurface, yellow dots here. Now, looking at the receiver and source array on the surface, and the source is a dynamite source in this situation. Sorry, a vibrocyte source in this situation. Standing in the middle, that's a split spread the array. This yellow spot serves as a common midpoint or common depth point between receiver 1 and the source. Okay, so at the position of receiver 1 and the position of the source, the yellow spot is serving as a CDP to them. Okay. By the time the source moves away from initial position, this is the first position, second position, first, second. By the time it moves away from to a different location, the receiver 2 becomes what? Starts using the same spot. The spot on the subsurface is stationary. It's not changing, but the receiver points is changing, okay? So when the receiver point changes, the source point also changes, which is your vibrocyte stroke has changed location. And now receiver 2 is now imaging the same spot and this CDP. Okay, so that means the second receiver is imaging this spot. When the vibrocyte stroke moves to a third location, a third receiver is now imaging the same what? The same spot on the subsurface. So this continues for the fourth receiver, fifth receiver, and then the sixth receiver. So what it means is that as your acquisition is going on, as you're changing the locations of your short points, because what is changing is mind you, for land acquisition, your receiver points are not changing. The receivers, when they are installed in the field, you do not remove them until you finish the acquisition. But your short points keep changing. So as the short points are changing, the CMP is being imaged, or the CDP is being imaged by different receivers. So the short point keep changing, different receivers are imaging the same spots. And so by the end of the survey in this cartoon, 5 different receivers were able to image the spot. So by the time on the last cartoon, no more receiver is imaging this spot. So what happens is that a total of 6 receivers were able to image the same spot in the subsurface, this stationary spot in the subsurface. So in essence, the fold of this data is a 6-fold data. Okay, so in reality, in the field, the fold of your seismic data is typically around 40, 50, and thereabout. So when you finish the acquisition, there will be what we call a fold map, which looks like this is your fold map, which looks like this cartoon on the right. So your fold map will typically look like this, and in the central part of the acquisition area, you will have the high fold. Okay, so from the legend on the right, you see that the central part of the data is having a kind of orange to reddish color. So the fold around here is about 30, maybe 35 folds. So this data is around the 35 fold data when it comes to maximum fold. And away from the center of the data, center of the field, the fold amount starts reducing. The data start what they call tapping out. So towards the flanks of your acquisition area, the image quality is most likely to reduce. And that is because the fold in those areas are reducing because they are the flank of the data. What that invariably also means is that if I can show this on a cartoon, when you have a receiver, a survey, your receivers are from the center, from end to end. As you're acquiring, the receivers in the middle regions, okay, are the ones that will do most of the imaging. The receivers are the flank, because they are the flank, their CMP, their midpoints will always not be that many. So they will have lesser amount of common midpoints as the source points is changing. That is why the fold at the flank or at the edge of your acquisition area is usually lower. But at the central part of the data or the acquisition area, the fold is usually high. And as at the central part that you're targeting your subsurface structures or whatever you're looking for, fault and fold and all that. So that is it for fold and what fold is all about. Then, is there any question before we proceed? Okay. So in the absence of any question, I've done the characteristics of the seismic data with you. We won't take much time on that anymore. Where I told you that your seismic data has to have a high signal to noise ratio. It has to have good temporal resolution and temporal and spatial resolution, and it has to have good spatial coverage. So in the last class, I explained that I didn't receive any much questions from that angle. So I believe that area is well understood. And then during acquisition, it has to be cost effective. You have to comply with the health, safety, and environmental standards, and even security standards for personnel working in the field. Most times, the field might be in remote areas. and you have to work within a specific planned schedule period. So you don't overshoot the schedule time, because if you do that, the costs of acquisition will also increase. So I also explained what signal to noise ratio means, where signals are the reflections that are coming from geologic boundaries, and noise is any other information that the geophones or your receivers are picking that are not coming from reflections of seismic waves. So I also explained the spatial coverage, where I explained using four receivers trying to image the structure, and you have a low image quality because you have wide-spaced geophones. But in a situation where you increase the number of geophones, your density of survey area increases, this receiver spacing also reduces. So you have more CMPs on the structure or CDPs on the structure. And by the time you increase the number of receivers, you also have more receiver CDPs on your structure, meaning that the structure will have a higher uh, fold coverage. And by the time you change the location of your source to a different point, you image the structure from a different angle. And that means also increase in your number of fold for this structure. And so your image quality will also increase. Then I try to explain good temporal and spatial resolution in terms of factors that affect this resolution. Number one, frequency, survey density as explained, short and receiver spacing as also explained. Then I try to explain your frequency and their contributions to your seismic data quality in terms of seismic data resolution. And I told you that the higher frequencies are frequencies of your seismic waves gives you a higher degree of resolution, but their challenge is that they die out quick. So the higher frequencies attenuate faster, but they give you more imaging of the subsurface, better imaging, especially in the first, maybe first 2 to 3 seconds of your seismic data. Then the low frequencies, even though they give you lower resolution, they have the ability to travel further into the subsurface. They do not attenuate faster. So because their wavelengths are longer, they image deeper, but the resolution at depth is usually poor. Okay, I tried also to use this cartoon to illustrate the effects of frequency in the subsurface, where you have a higher frequency on the right and low frequency wave on the left, passing within a specific period that I marked with red lines. And here we identify we have just one head within this area, okay, within this period, here to here. And also here we have about 3 heads. So this is a higher frequency, and it gives you better imaging of the geology around this area. Then I use this also to illustrate 2 seismic data, where one on the left have a low frequency bandwidth between the dominant frequency between 7 and 33 hertz, as shown in the frequency spectrum on the base. And the one on the right has a higher frequency bandwidth between 1.6 to 53.8 for your dominant frequency. And if you look at the 2 data sets closely, uh, you will find out that the one on the left has a lower resolution than the one on the right. For instance, the one on the left, if you look at this area that I'm using the red, I'm circling with the red. If you look at that area, you see that there is poor imaging behind this fault. So you can see there is no much where the fault they call the dung fault. There's poor imaging around here. Okay, let me use the laser pen. So there is poor imaging around here. You cannot see image continuity. There is chaotic reflections around here. But look at the same data on the right. You see that there is less chaotic reflections on the right on that same area within the same data set. Why? Because probably they were processed by 2 different persons, and the person on the geophysicist that did the processing for the one on the right his dominant frequencies and also the low frequencies. And so the image quality is better than the previous one. And also, if you look also closely to this part of the data again, top left part of the data, if you were to compare also this side, you see that the amplitude of this region is low. You have very, very low amplitude. Okay, but if you look at the same data on the right, you see that the amplitude is higher within that region. So there is event continuity around there. And so if you look closely again, so many other places within the data, same data sets, you find out that there is low amplitude in the one on the left and high amplitude in some areas on the one on the right. So these are the effects of frequency. You can see more event continuity on the image on the right, more than the one on the left. For instance, in this area, I circled red. Look at them also in this area. So there's better image continuity, event continuity on the one on the right than the one on the left. And so that is the effect of your frequency on your seismic data and its resolution. Try to do a little class work where we try to calculate frequency in terms of apparent and dominant frequency using oscillations of our seismic wave that we are seeing in terms of the peaks and the troughs. We also did some assignments in the class, and you guys did and submitted your assignments, and you all did well. So thank you for that. Lastly, we talked about acquisition environments from land acquisition to on land. We talked about different environments, swamp, swamp, desert, mountainous regions, forest, and all that. We talked about the acquisition sources for land, which is mostly the dynamite and the vibrosize. And we discussed about their few advantages and disadvantages. Then we looked at the land source, receiver rather, which is the geophone, which we all are conversant with. And then we looked at the nodes also. We have different node types depending on the company that designed them. And then the advantages of the nodes over the geophones, because they have the ability to record and give us information in real time. And they do not use wires and cables, and so they have less environmental interference and all that. Then we looked at the marine acquisition. In terms of the source, we talked about the air gun, okay, as a source, predominant source that is used in marine seismic acquisition is the air gun. Then we looked at the receiver, which is number one is the geophone, the hydrophones that are encased within the streamer lines, okay, and they are spaced as required within these yellow tubes, which we call the streamer. And the streamers float on the ocean surface as shown on this image below, and they are towed behind an acquisition ship or acquisition vessel, as it's called. Then I mentioned about another offshore acquisition receiver, which is the ocean bottom nodes. So like the land nodes, they are placed at the bottom of the ocean, and the importance is that it helps to reduce noise in your seismic acquisition if you're using the nodes. For instance, while what that means is that if you're using the streamers, for instance, if you shoot the seismic from here, the seismic wave have to go through this water column, get to the ocean floor, travel through the surface, and get back to the surface, and then come to the receivers, okay? So the ocean water interferes with this seismic wave as they travel. And so it introduces a lot of noise. There will be noise like multiples and all that were introduced in great amounts into your data. So the ocean bottom nodes eliminates that because they have to go to the ocean ocean floor and place the nodes as shown in this cartoon. So when the seismic wave energy is generated as shown by this cartoon, the wave travels into the subsurface, travels through the water column, gets to the subsurface, and then travel back without going back into the water column, it just gets received by the nodes that are already at the ocean floor. So the nodes are designed in different sizes and different shapes, as shown in the cartoon on the left, or the picture on the left. So the only setback with the nodes is that they can be difficult to deploy because they are deployed at the ocean floor. So you need special equipment, special tools, and specially trained technicians or experts to go and deploy them. Secondly, you don't get your data in real time with the ocean bottom nodes. So the ocean bottom nodes records and store the seismic data within them. And so if anything happens and you don't stick to the planned time of acquisition, and the batteries of the nodes died out, it's a big problem for you because they have batteries in them. So you have to work within the time frame of their batteries so that they will keep recording while the battery lasts. So you don't get your data in real time. You have to go retrieve your nodes and download the data from them. So that's majorly their setback. Then the ocean bottom cable, just like on land acquisition, the cables are installed at the bottom of the ocean, just like you have your geophones and all that. So you install them at the bottom of the ocean, connecting the receivers with the by cable to each other. So we call them the OBC. So this is OBC. So if you're in a place and they mention OBC acquisition, know that they're talking about ocean bottom cable. And for this one, it is called the OBN acquisition. Okay, OBN. So if you're in an environment or you're in a company and they are talking about their data sets and they are talking about OBN, just know that they are talking about ocean bottom nodes acquisition. So the nodes, ocean bottom nodes were used for the acquisition of the seismic data. And when they talk about OBC, so you know that they are going to use ocean bottom cables or they have already used ocean bottom cables. Okay. So that is that for that. We also talked about few of the advantages and the disadvantages of the ocean bottom cables. Disadvantage is that they are difficult to deploy, okay? But they can record both your S and your P waves, okay? You know that your S waves do not travel through your through fluids, so they don't travel through the ocean water. So if you want to deploy, you can deploy the source at the bottom of the ocean as well. So you generate both your P and your S waves that goes through the subsurface, and when they come back, they are picked up by this ocean bottom cables that already have the receivers in line with them, just like your geophones. So another huge advantage of the nodes and the cables is that they are flexible. During acquisition, okay, for instance, if you have an oil rig, you all know what is an oil rig. So if you have an oil rig here in the offshore environment, during acquisition, they do not do streamer acquisitions around the rig. They avoid the rig for about maybe 100 to 200 meters from the rig. There's no acquisition with streamers near the rig. So assuming this my box here is a rig, you don't bring a streamer vessel around it. But if you're using OBC and OBN, what it means is that the sea floor around this area will not be imaged, okay? The seafloor around this area will not be imaged because there will be no receiver lines crossing this area. So, but if you're using OBN or OBC, you can always put your receiver lines crossing near the platform or the offshore rig and without any effect or any damage to the rig. But the acquisition vessels usually avoid the rigs. So that's also a major huge advantage of using OBN and OBC. So it gives you flexibility of acquiring everywhere in the seafloor without fear of being close to a rig or far from a rig and all that. So that is it, and a recap of what we've done. So I want to talk about the dimensions of the seismic survey. and which is where we'll end our discussion on seismic acquisition. And then next time I will take you through processing. I'll give you an overview. It's not part of Lecture Hub's requirements. They talked about acquisition and interpretation, but I'll brief you on processing before we go into interpretation. So for the seismic survey, there is what we call the dimensions of seismic survey, where we talk about the 1D, 2D, 3D, 4D, 4C, and all that. So we'll look at that briefly for today and before we call it a day. So the first one is the one-dimensional seismic survey. What do we mean by one-dimensional seismic survey? Okay, is the seismic survey that is carried out within a well bore. Okay, a company drills an oil well. Okay, and within the well, they go and acquire seismic data inside that well. Okay, now why? Your well is measured in depth. Okay, your well is in depth and in the Z direction. Okay, your well is in depth and in the Z direction. So you put your receivers inside the well. So you know that the well has crossed different formations that has been identified during drilling. So within the well, they will install the receivers. So the receiver in this case could be your geophone or maybe your hydrophone. If the well still contains drilling fluids, could be your hydrophone. And so they go to the well and then they install the receivers at interval. Most times they install it to correspond with reservoirs or formations of interest rather. So what happens after installing the receivers within the well, they now shoot the source on the surface. So the seismic wave travels straight to the receivers from the source, just as shown here. And there are two types of one-dimensional seismic survey. One is the check shots, and the second one is the vertical seismic profiling, what we call the VSP. The vertical seismic profiling or the check shot. What is the difference between the two of them? The two difference is simple. For the check shot, the source, when shoots shots on the surface, the seismic wave travels straight from the source to the receivers downhole. So the receivers are already in the hole or in the well bore, and the seismic source, when shot, it goes straight to the receivers. So you remember in our seismic acquisition, seismic method class, where I told you how seismic waves are generated, that from the source to the receiver, the seismic wave will travel to the boundary and reflect, right? And when that happens, it's doing that as a common midpoint, okay? We all know this already, which is the CMP and or the CDP as it's called. So what happens, we remember we also discussed about the two-way time, meaning that the seismic wave traveled from the source to the geologic boundary and then reflect back. This is downward motion and upward motion, and reflect back to the receiver. So we call it the two-way time, right? But for our one-dimensional seismic, we are not interested in the two-way time for the check shots. We're interested in what we call the one-way time, OWT, one-way time. So if you're doing seismic interpretation and you're dealing with your check shot, you will see that the check shot will be written as a one-way time data, meaning that the seismic wave moved from the source straight to the receiver. It didn't reflect back. Okay, so that's what the check shot survey does. Why do we do this? We want to measure the travel time of the seismic wave to this receiver. You remember you've already placed the receiver within the well bore at intervals of interest, for instance. So you already know the depth that the receivers are placed. Maybe this one is placed at 100 meters within the well bore. This one is placed at 150. This is at 200 and all that and all that. So you already know the depth in terms of Z direction, which is the same thing as distance. Okay. So when you shoot the seismic wave, on the surface, you're trying to measure the time that the receiver 1, which is at 100 meters, will pick up the seismic wave. And the time receiver 2, receiver 3, and so on and so forth picks up the seismic wave. So in other words, your receivers will record your time for you. And so you know that velocity is equals to distance what? Over time, d over t, okay? So you already have your distance. You're the one that placed the geophones in the well, so you know their depth, which is distance. Your geophones in the well has already measured the time of arrival of the seismic wave in one-way time. Then you have to measure, you are now going to interpolate the velocity. So with that, you will know the exact velocity that this, you know that you place your receivers within maybe formations of interest. So you will know the exact velocity of travel of seismic wave to this particular formation of interest, okay? Which could be your reservoirs and all that. So in other words, you're getting an accurate velocity information of the subsurface. Okay, so what happens is that your 1D survey are used to determine the sonic velocities of strata penetrated by well, okay, and allow more accurate time to depth conversion. So you need this. Remember also that your seismic data is recorded in time. So you need your check shots, which is gotten from a well that is drilled and recorded in depth to convert the seismic data from time to depth. So you need this velocity information you generate here for your time to depth conversion, okay? So that is it. That is it for the check shot. The VSP does the same thing. The second type of one-dimensional survey, it does the same thing as the check shot. But the only thing different is that the VSP measures both your one-way time. You can see the legend here. You have the green arrow showing you one directional wave that move from the source. This source here is a vibro-sized source, for instance. Your seismic wave moves straight from the source to the receiver at the subsurface. So it measures your one-way time, okay? And it also measures your direct, which is your direct arrival, your one-way time. It also measures multiples. So any multiple events in terms of waves, seismic waves, the receiver will also record it. You can see the downgoing multiple and upgoing multiples shown. And then it's also measure your reflected wave, which is also your two-way time, okay? So the check shot measures both the VSP rather, not check shot, measured both your one-way time and your two-way time. So the seismic wave can travel from the source to a particular formation boundary and go back to your receiver points, okay? So that is it for your VSP. And if you look closely, you find out that for the VSP, it seems that the receivers are placed within a particular formation. So if you look well, you can see that the receivers are clustered just around these sand units, okay? They are clustered. So the paramount interest is on maybe this is a reservoir, okay? So your paramount interest is on the velocity of this particular reservoir. And you place your receivers at interval within that reservoir and then shoot your VSP to measure and get the accurate velocity reading within this reservoir. So it's also used for advanced reservoir studies for purposes. But for your check shots, you can place your receivers at a regular interval, irrespective of formation type, be it receiver, be it reservoir, be it source, or whatever. So that is majorly the difference between the two of them. But they both serve the same purpose. They are giving you velocity information of the Earth's subsurface and more accurate, in other words, more accurate velocity information that is used for your time to depth conversions. So there are different geometries that are used for your 1D seismic acquisition. So here, there are different ways. You can be acquiring your 1D within a straight well or within a deviated well. It doesn't matter, okay? So one is the zero offset VSP or maybe zero offset check shot. You have within the well, your receivers are within intervals, placed at interval within the well. And you shoot your source very close to the wellhead, okay? Almost at the point, at the mouth of the well. So that makes it a zero offset. because if you have your receivers here and your source here, okay? The source is away from the receiver, and the distance from the source to the receiver is your minimum offset. Okay? Distance from the source to the first receiver is your minimum offset. And distance from the source to the last receiver is your maximum offset. Okay? So what zero offset means is that you're trying to place the receiver and the source on the same spot. In terms of there's zero offset. They are both on the same location. So that's what this particular VSP, zero offset VSP is trying to mimic. Okay. Any issue? I'm hearing background noise. Please mute your mic if you're not speaking. So second, we have the offset VSP where the receivers and the source point is away from the the wellhead or the well top. So for that occasion, you have an offset VSP, like shown in the cartoon number B. For cartoon number C, it's just the same thing as the first one. The first one is for a straight well, and C is for a deviated well. D is also for a deviated well for offset. So and E, the same thing for maybe a horizontal well in a situation where there's a horizontal well. Then there's also what called the drill bit listening. You can use the 1D seismic during drilling operation to do your formation evaluation while drilling. Where a situation where within the well, you have the drill bit carrying out the drilling operation, and on the surface, they put the receivers, okay? What they are trying to do is because the drill bit generates some kind of noise, which is a wave, or a sound, which is a wave. So you're using receivers on the surface to listen to the arrival time of the sound from the drill bit. So this is a drill bit listening survey. So it's also a type of 1D survey. So they are using it for formation evaluation while drilling, okay? Or measurement while drilling purposes. The other one is the walkaway, where you have the source with the borehole. This is for G. The source and the borehole, while on the surface, you keep moving the short points away from the zero offset. Okay, you can have that for a straight well and for a deviated well. And also we have a walkover VSP, where mostly use the walkover VSP is mostly used for deviated well, where you have your short receivers within the well, and directly above the same offsets where the receivers are, you place your shots. Okay, so it's more like walkover VSP and also a zero offset VSP. So it's a combination of the two. So all these things, all these different techniques, what are they doing? They are just trying to get better or accurate velocity information of the subsurface lithologies, or maybe lithologies or formations of interest. So the other thing I'll point out is on the surface, you can see the different geometries that they also use. You have the gridding, you have the radial, and you have the spoke type geometry, where they are all in the geometry types I've explained. On the surface, they can be using a different arrangement for acquisition of this 1D survey. So that is this for one-dimensional seismic survey. The next we will look at is the two-dimensional seismic survey. So what is the 2D? I'm sure we are all conversant with the 2D. We've all heard of it one way or the other. It's a seismic acquisition survey design where you have one receiver line, okay? You have just one receiver line. So on that receiver line, you also have your shots on the same receiver line. So like on the first one, you have your receivers that are placed 1, 2, 3, and to the last one, N. at a regular interval. And on the same line, you keep placing your shots in between the receivers. Okay. So the short points, which is this, is placed in between what? The receivers. So for this occasion, it's called the non-coincident geometry design for 2D acquisition. Okay. And another one is the coincident geometry type, where you have the sources corresponding on the same location or the same spot with your shots. Okay, so it kind of operating a zero offset with a particular receiver and maintaining a regular receiver and shot interval anyway. So for that, it's called coincident geometry, and the first one is non-coincident geometry. So what is unique about the 2D seismic acquisition is that it's majorly used for regional or reconnaissance studies within a region. Okay, it's normally used for regional studies, and it's usually cheaper to acquire surface. So for your 3D acquisition, let me get the red pen. For your, 2D acquisition, you get one data set like this at the end of the day. Your stack section will be one data set that is measuring your X, which is your offset, and your Z, which is your depth, okay, or your time. So you have your seismic data recording from 0 time to maybe 0 to maybe 6 seconds, okay, in the subsurface, and then it will record the offset from receiver 1, 0 offset to the last offset on the surface. So it gives you your, in this case, it's giving your X and Z direction, what you call your XY, okay? And simply you can call it the XY, but here is Z because it's your depth. So it's used for regional studies, as I mentioned earlier. What do I mean by regional studies? For instance, you have a block, your company has an oil block, and you have to do your geophysical survey within this block. What happens is that you're going to run it will be quite expensive to run 3D seismic acquisition over this block. Let's assume this block is, just as we said before, 75 kilometers long and 50 kilometers wide. 50 kilometers wide. So that's about 35,000 square kilometers, Abi, if I'm not mistaken, or more than that. Somebody can calculate and tell me the exact size. So the block is quite big, and for that reason, your company will find it quite expensive to start acquiring seismic data over this whole of the block. Okay, it's going to be very expensive to acquire seismic data over the whole of the block. So what do you do? So your total area is 3,750 square kilometers, okay? So it's going to be quite expensive to acquire. And you remember your petroleum geology, you're interested in subsurface structures, assuming this is a petroleum province and you have a block, let's say your OML10, as we discussed earlier. So your company wants to acquire a seismic in this area. It will be quite expensive to acquire 3D seismic over this 3,750 square kilometers. What do? You run 2D seismic surveys over the place of the region. So you run your 2D like this, just scatter 2D lines over the place, any direction you like. Remember, your 2Ds are just one line, so they are cheap. They are cheap to do. So you can run your 2D in depending any length of the line you want. So you keep scattering the 2D over the area. What are you looking for? You are looking for, in this your 2D result, which is on the I've sketched on the far right. You're looking for a structure, maybe a fault, or maybe groups of faults, which will become your prospects. You're looking for a group of faults, or maybe a fault that will serve as your prospect within this region. that can become potential traps for hydrocarbon, right? So what happens is that you have your 2D scattered all over the place. So out of all these 2Ds that were acquired over a particular period, maybe 1 or 2 years period, you found out that maybe it is only this one here, the one I've drawn with a green line, that saw a structure, this particular structure on the I've sketched on the right, on your 2D stack section. Just this stack section will just be only this one. Just like for one of my intents, I described the 2D as you are having a loaf of bread, okay? That's one way I try to describe it for my students. You have a loaf of bread, for instance. And do you remember when I mean a loaf of bread, I mean a loaf of sliced bread. I imagine that that loaf of sliced bread is the soft surface, okay? And you are to remember when we were kids, I don't know about you guys, bread used to have these raisins within them or fruits. And so when they are giving us bread in the house and it's sliced bread, we are always interested in those fruits within the bread. It's small, small kind of fruits, small sizes. They call them raisins or something within the bread. So we're always very interested in getting the slice that contains those raisins because they are very sweet and sugary. So imagine that those raisins within the loaf of bread, you know, they are not in everywhere in the bread. They are scattered within the bread, and they are not everywhere, so they are scarce. So any slice of the bread that contains the raisin is a treasure to you, as for me then as a child. So what happens is that when they drop a loaf of bread, we start searching the loaf of bread for the one that will contains it to take. Now, imagine that that's resin within the bread, your slices of bread is your oil field or oil accumulation in the subsurface. So what happens is that when you get the loaf of bread, which is assumed to be the Earth's subsurface, your 2D line is like taking a slice of that bread. So you have a loaf of bread, but you are limited to only one slice of bread. So that's what 2D line is like. You're taking a cross section, just one cross section of the Earth's subsurface. Within the region you run your 2D line. It doesn't matter the direction you run it. Just one cross section within the area you run that 2D line. So that one cross section is like looking at a slice of bread to see if it contains that resin. And in this case, to see if there will be an outline of a structure. So like our cartoon here, the outline of a fault or the outline of an anticline, an anticlinal structure that can become a potential trap for hydrocarbon. Okay, so if you run all your 2D lines over your block and you identify maybe one or two of the 2D lines, it's showing you prospects, okay? It's showing you that there are structures within these places that could become or it's giving you leads. That's what the right word, leads that can become your structures. What do you now do? You now call, instead of running your, let me get a highlighter. Instead of now running a 3D over the whole area, you now run a 3D over the region where the 2D is located, okay? Just as I'm highlighting with red, yellow. So you now do a 3D survey over this area that you have seen the structure with the 2D. So what did the 2D do for you? The 2D helped you to have an overview of the whole subsurface within the block. You are running it in, you scattered it, so like, okay, I've explained this already. So like you have a block. So like as shown in this image, we have this block as shown in this image. You can see they run so many 2D lines on it with different coloration representing during different time frames for the acquisitions. The green, the red, this. So any of the 2D blocks, the 2D lines that gives you the prospect that you're looking for, it gives you a lead rather. You can now run that gives you a lead. You can now use the lead information to run a 3D around where the region, where the 2D is showing you the lead. So you can run a 3D around here and say maybe a particular 2D in this area showed me something, a lead in terms of structure that can help me, that should be properly investigated. So that area will now run a 3D around there. So your 2D is usually used for regional studies or reconnaissance studies. Okay. over a large area, over the basin, over your block, or and thereabout. So that's it. So for your 2D seismic data, remember it's a straight line, one line data. One line, just as shown here, is just one line with your receivers on the straight line and then your source on the same line as explained. So the data you get from your 2D will just show an outline of the receiver line as shown on this image on the right. So you have your 2D line on the surface, your seismic data in time will give you just an outline of the 2D data this way. Okay, so this is what your seismic data will look like when you finish your 2D survey. This is a typical short gather of your 2D seismic survey. This is what it will look like. This mound shape structure, that's your data, your 2D data. This is what it will look like, only this. And it will be depending on the number of shots that we are used in the acquisition. That's number of shots, when I mean shots, sources. So if the shots along this receiver line, if they use the 1,000 shots, okay? So you have this in 1,000 places, this mound-shaped structure, which is your shot gather in 1,000 places. So you have the shot 1, shot 2, shot 3, shot 4, up to 1,000. Now, looking at it, why is it shaped in a mountain or hilly shape like this? Why is like that is because the center of it is where you have the source. Remember your split spread arrangement that I showed you before, which is shown here. The source is in the middle and the receivers are spreading on the left and on the right. So that gives you what? A split spread array in terms of the geometry, okay, of your 2D acquisition. So in this case, you have this mound shape because the source, which is at the center, is at the center, which is the source is at the center of this acquisition. So while you skip from shot to shot, you keep getting short gathers that will look like this, okay? Short gathers that look just like what you have on the screen. So that is it for a 2D seismic data. It's cheaper. You use it for regional reconnaissance over large areas. And when you get a lead from your 2D, you can now use your 3D for better imaging of the subsurface. So that's that for 2D. So for your 3D, the aim, just as I said earlier, is to get a higher degree of resolution of the subsurface. So just as said, it gives you better imaging than the 2D. The 2D gives you a one-line data, sorry, a one stack section of the subsurface. But your 3D gives you more stack sections, not just one, multiple stack sections. Because you remember your 3D, you have multiple receiver lines, not just one, multiple receiver lines and multiple sources crisscrossing the receiver lines, okay? So your 3D survey samples the volume of the subsurface. So for the 3D, it's like having the whole loaf of bread, just as I used it for illustration before. Your 2D, you're having just one slice of bread out of the whole loaf. But for your 3D, you're having the whole loaf of bread, okay? So within the whole loaf of bread, you can pick up any slice and look for the treasure inside the slice. You can pick up any slice of interest and look for the raisins that are the sugary, fruity raisins within the bread, which is your treasure that you look for. We look for those days as children. So your 3D is like having the whole bread, and that is why it's called a volume. What does that also mean? It means that your 2D, you don't just have your X and your Z, as I illustrated earlier. You don't have your X. You don't just have your X and Z. You have both your X, Y, and your Z. So you have your data as a volume this way. You have your data as a volume. So you have your X, you have your Y direction, you have your Z, which is your time direction or your depth direction. So you have a whole volume, which is synonymous to a whole loaf of bread, as I try to give an analogy of that. So for your 3D, as we know already, you have a cross line, receiver line, multiple receiver lines, and then your cross lines, crisscrossing the receiver lines, okay? That is for land data. But for the marine data, you don't, you just have the receiver lines, okay? Tagging behind a tugboat or a acquisition vessel. And okay, and the air gun standing in front between the tugboat and your receiver lines. So that is it basically for the 3D. So on the 3D data, there are different acquisition geometries that can be used. Okay, this is about 3 of them. The orthogonal geometry, where you have your receiver lines, okay, and perpendicular to the receiver lines, you have your source lines, okay. And then you can also have your receiver lines, and instead of having the source lines perpendicular, you have them at an angle. They are placed at an angle, slanting angle to the receiver lines. So this one is a 26.5 degree slanting receiver angle geometry, receiver source angle geometry. Then you have the brick pattern where you have your receiver lines. Remember in acquisition, especially for land, your receiver lines are stationary. You plug your geophones and you leave them. This what is changing is the source line, is the source point, and the source point will follow this arrangement. For the brick geometry, it will follow this pattern. This could be your source 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the continuous, and so on and so forth. But for the orthogonal one, you start from source 1 to source n, and then continue n1, and so on to maybe nz or whatever, and continue in this order. So it will take maybe this configuration. You follow this configuration for your source and keep changing their locations, okay, until you finish the acquisition. For the slanting, you can take the same configuration until you finish. But for the brick pattern, can think they go something this way, and maybe join this one and continue. So somebody may now wonder, why are they changing the geometries for the 3D seismic acquisition? The essence of changing the geometry is that one of the things that's qualities or characteristics of a good seismic data is that it has to have high signal to noise ratio, right? High signal to noise ratio, okay? Your signal to noise ratio will be should be high, in the sense that you record more of the reflected seismic wave than more of noise. So the more your signals, which are the reflected waves coming from the geologic boundaries, should be more than the noise that you're recording. So the geometry that they are choosing is for the acquisition, or is aimed at maintaining a high signal to noise ratio. So they can look at the topography of the area. They may look at the topsoil geology. They may look at different factors and decide which of the survey geometry to adopt. The essence is that they want to suppress noise during the acquisition. They don't want to acquire so many noise and record it into the acquisition. So during acquisition, they can choose any of these geometry in order to increase the signal to noise ratio of the seismic survey. So for land acquisition, for 3D, this is typically what it looks like. Your receiver line. Okay, so for land acquisition, this is typically what it will look like. The geometry will look like for an orthogonal acquisition design, geometry design. And here is what the receiver arrangement will look like. Okay, receiver lines, then the short points will crisscross across the receiver lines, okay, at a regular interval of choice. For the marine acquisition, for the 3D, is the same uh, receiver lines following a straight line, and there are different receiver lines. For 3D, for 3D, it's going to be up to 4, 5, 6, 7, 8 to 10 or 20 receiver line, depending on the plan. So you can see from the image on the far right, the tugboat is towing a streamer line, and you can count how many streamer lines that are here in this acquisition. So within the streamer lines, you have your receivers, and then following behind, between the receiver and the boat is your air guns. So the air gun, you fire the air guns, and the seismic wave travels and reflects, and the receivers behind pick them up. So for this one, you don't have a split spread array. What you have is an ended one-ended side array. So your seismic data will kind of have a different shape than what we know earlier. So this is a typical land seismic acquisition. You can see your mound shape structure as I showed before. Because it's 3D, there are going to be more than one of these receiver lines uh, bonded together, and they will have these mound shapes as shown here. So anytime you see your short girders, this is a typical short girder for a 3D seismic data on land. Anytime you see this, you know that it's a 3D survey. But if it's a 2D survey, it will just be only one of these mount shapes, okay? It will just be only one, just maybe only this one, the first one. There won't be the rest. And the number of these mount shape structures will give you the number of receiver lines that were used for the acquisition. So for this one, there are about 6 of them. So that means there were 6 receiver lines for the acquisition where this data came from, okay? If you have 10 receiver lines, you have these mount shapes in 10 places. You have them in 10 places, each of them representing what? A receiver line. And in each of the mounts, shapes or the gather rather, you have individual what? Seismic traces coming from individual receivers or geophones for the receiver line. We all know how we generated our seismic traces during our seismic geophysical method training or discussions. So that is that for 3D survey. Then the last thing I'll mention about the 3D survey is that I've also mentioned that already, that the 3D will give you your X, your Y, and your Z, okay? X, Y, and Z, okay? So in essence, your 3D data is giving you anything that has 3 dimensions is a volume. You know, in elementary mathematics, you can only measure the area of a square. Okay, but when you talk about a cuboid, you talk about what? The volume. So the area is length times breadth for square, but for a cuboid, you talk about length times breadth times height. Okay, or length times width times height. So that is what happens in seismic data, in 3D seismic data. You have your length and your breadth and your height or your depth in this case. So it gives you a volume or a cube of the subsurface, a whole volume of the subsurface or a cube. So you're in a situation or you're a place or you're in an environment, you're in a company, and they are talking about, one of your senior colleagues is telling you about seismic volume. He's talking about the seismic volume. Please do not get confused. A seismic volume is a 3D seismic data. A seismic volume is a 3D seismic data because it's just as I explained what a volume is all about. So because I've explained what a volume is all about. So your 3D data will give you your volume, your length times breadth, and your height. So somebody can also say seismic cube. They're also talking about your 3D seismic data. So for your 2D seismic, you don't get a volume, you don't get a cube. okay? You only get one single stack section, okay, or one single cross section of the subsurface, which is your stack section, just one stack section. But for your 3D seismic data, you're going to get multiple stack sections or multiple cross sections of the subsurface. So you see this cube now, you can take this cube, you can divide this cube from every side, you can cut it from here, cut it from here, cut it from here, cut it from here, which are in line with your receiver lines and your short lines. Or you can also decide to cut it in this direction, okay? And you can also decide to cut it horizontally in this direction. So that is what the image on the right is showing. That for your 3D seismic data, you can have your inline, and you can have your cross line, and you can have your time slides. So you can be looking at the data in the inline direction like this. You can be looking at the data in your cross line direction like this, or you can be looking at it from the vertical direction, which is your time slice, from above, your Z direction. Or you can be looking at it from your X direction, which is your inline, or your Y direction, which is your cross line. So for the seismic volume, your 3D volume, you have different receivers, different inlines and different cross lines that you can look at for the data. So this is typically what your inline and your cross line will look like for the image on the right. So this one could be your inline, and this one will be your cross line. So you're looking at the data from the inline direction and from the cross line direction. And you can also look at the data from your time slice direction. So it's like looking at getting a plain view of the data. And for the time slice direction, you can choose any time from 1 second to 500 to 1,000, 2,000, any time of interest. You can just cut the data from that time and look at the data from that direction. So that is it for our 3D seismic volume. And with this, it gives you a better image of the subsurface, okay? Because when you look at a particular inline, you see the structures that are within the data. For instance, if this is your inline, you can look at it and you see maybe your fault is here. You go to the next inline that will cross the data from this side, and you also look at the data from that inline and see if that fault occurs there. You can also map the faults there, and you cross over to the next inline and continue that the way and so forth and so on. That is how the 3D data and its major advantage in terms of resolution and better imaging of the subsurface. Okay. The next one we will talk about is the 4D seismic data. The 4D seismic data. What is the 4D seismic data? Anytime you talk about D, remember we're talking about dimension. Anytime they are talking about D, whether dimension in seismic. If they say 1D, you know what they are talking about. They are looking at only the vertical, okay? Only the vertical is the direction of paramount interest. When they say 2D, okay, 2D, your vertical and your horizontal is the directions of interest, okay? When they say 3D, your vertical, your horizontal in X and Y are the directions of what? Interest. Now, what about the 4D? What is the directions of interest? In the 4D, your vertical, your horizontal in X and Y are of interest, but you're going to do ×2 of it in two places. So you repeat your vertical and your horizontal in X and Y's over a period of time. That is what I mean by in two places. So your 4D seismic simply means your 3D seismic over a period of time. So you have two 3D seismics recorded over a period of time. That period of time, which introduces the factor T, time, that is the fourth dimension of the 4D seismic data. So your 4D seismic data have your X, your Y, your Z, and your time factor. Okay? The time factor. That is what makes it the 4 dimensions So what does it mean? It means that you're repeating a 3D seismic data over a period of time. So a company has a block, as we know, understand this very well, and you acquire seismic data in this block, in this whole block, okay? You acquire seismic data in this block, for instance, in the year 1995, okay? If you go back to that same block in the year 2025 and acquire another seismic data on the same block and exactly on the same place you acquired it before, using exactly the same parameters you used to acquire the seismic data before, parameter in terms of receiver spacing, short spacing, receiver location, exactly the same location, no changes. So you look at the acquisition report that was used in 1995, and you say receiver 1 is on this point, receiver 2 is on this point. So you go back in 2025, you place receiver 1 in exactly the same point, place receiver 2 in exactly the same point, receiver 3, and so on and so forth. And you shoot your dynamite or vibro size. If it's dynamite they used before, use dynamite. If it's vibro size they used before, use vibro size. And you shoot it exactly where you shot it before, using the same amount of dynamite. If they used 20 kilogram, if they use the 5 kg dynamite per shot, or maybe 2 kg dynamite per shot, 2 kg is a lot of weight. 2 kg amount of dynamite per shot, maintain the same 2 kg dynamite per shot. If they anywhere they drill the short hole before, drill your own short hole there and repeat the acquisition as accurately as possible as it was acquired 20, 30 years ago, 10 years ago, whatever, and repeat the same acquisition. That case, you are doing a 4-dimensional seismic. You are repeating the same acquisition that was done 10 years ago, 20 years ago, 5 years ago, on the same spot, using the same parameters, not changing anything. Okay? The essence is that you want to compare the data before and after. Some of us used to do the before and after challenge. You put your picture in when you're in secondary school, and then you put another picture when you're in year 1 in the university, and put another one when you're in final year. By the time you're in final year, you're not a fresh boy. You know what I mean? Maybe you're year 1, you're looking very slim and lanky. But in your final year, you're not looking very robust. Some people will put before and after picture of when they were in Nigeria and when they have Japa and when they're in UK and Canada or wherever. That is a typical, what they are doing is typical time-lapse picture comparison. They are comparing their picture when they were in Nigeria to their picture when they're in the UK or America or anywhere. Or you are comparing your picture when you are in 100 level to when you are in 500 level in the 400 level in the university, to compare and see how you have developed as an individual, how you have grown, how you have changed in terms of physique, in terms of appearance. Some of our ladies will turn from dark complexion to yellow complexion or fair complexion and all that. We all know these things. Some of our guys will come from low cut to dreadlocks. These are changes that have happened over 5 years in your life, 3 years, 4 years, and all that. So the same thing happens in seismic acquisition. You are comparing the subsurface over a period of time. So you want to see in 2020, 1995, we acquired seismic data, drilled our well in 1996, 97, and we have been extracting oil from our reservoirs for the past 10 years. So you want to acquire seismic data there again and compare the subsurface data to see how far the subsurface geology have changed in terms of the fluid content of the reservoir. How has it changed? Have there been depletion in the reservoir? Have there been, how has the reservoir changed? So the 4D seismic is used for reservoir monitoring majorly, okay?
I'll be past it.
They are basically used for reservoir monitoring. We have barely 20 minutes. And so it's very important you use it to monitor your reservoir, use it for enhanced oil recovery. You want to know where to inject, do gas or water injection and improve reservoir productivity. You want to know where you have bypassed the reservoir oil in the reservoir. Maybe some reservoirs you bypass them within the reservoir. Are they communicating across faults and all that? These are the essence of doing your 4D time lapse seismic. Or when you and then another thing is that anytime you hear time lapse seismic, time lapse, so time lapse seismic, just know that they're talking about 4D survey. So don't get confused. It's just they're repeating a 3D survey. Okay. They can be doing this for time lapse survey using OBN. They can be doing it with OBN. They can be doing it with OBC. They can be doing it with streamer. So most of the IOCs that have the deep offshore, they are using OBN and OBCs and OBC survey. They will also be doing this time-lapse seismic. So they can be using OBN, they can be using OBC and all that. So it doesn't matter. Okay, somebody asked a question. If 2D is a line and 3D is a volume, what is 1D? Okay, 1D is also a line, but only in the vertical direction. Okay, it's only giving you information in the vertical direction. Somebody asked the question. It's not giving you the information in the vertical and the horizontal. So your 1D is looking at the Z alone. So within the Z direction, which you have your depth, you will now get record velocity informations at interval, okay, with respect to depth. So it's not going to give you this velocity information with respect to offset, okay? So that is why the 1D does. It gives you in one direction, which is the Z direction. So I think I've answered that one now. So that is it for your 4D seismic. Is used for subsurface reservoir monitoring. So we'll quickly look at example of where they have been applied. For instance, in the picture or the cartoon, sorry, the seismic section we have in front, not a cartoon, gotten from a particular place. The upper part, which is the part A, was seismic data acquired in 1989. And you can see this flat spot. You can see this red event, which is your trough, showing a flat continuous trough, okay, interpreted as a oil-water contact. Okay, now after 1990, by 1998, which is roughly 10 years after the first acquisition, the acquisition was repeated. And you can see that the amplitude of this oil-water contact has diminished. Here, the amplitude is very strong, meaning that there is a strong oil-water contact. So above this contact, you have your oil accumulation. But here, the oil-water contact has diminished, meaning that the oil within the reservoir here has depleted. If you are to put a straight line or a ruler across here on where you have this flat spot, you will see that the flat spot corresponds to about 2 seconds within the seismic data. If you come here and try to identify these same flat spots, you find out that the flat spot has almost disappeared. But where you have a slight outline of this flat spot, if you put a ruler to it, it will not correspond to 2 seconds. It will not. It will be corresponding to maybe 1.9 something second. What does it mean? It means that the oil, you have depleted the oil and water within this reservoir has gone up. There's currently water flooding within the reservoir in this area, what we call water flooding. So the oil and the oil-water contact have actually moved upwards to somewhere here, okay? So that is typically what this time-lapse seismic is showing or is interpreting. Another one, we can also look at the image here. On the one on the left, the data above was, the upper part was acquired 1985, and the one below was acquired in 1996. You can see that on this interpreted horizon, the amplitude here was not continuous. There's amplitude is not continuous, but after about 10 years or thereabout, the amplitude becomes more continuous. okay, which shows a change within the reservoir. The change can be interpreted by geologists to mean anything. Could mean depletion of oil and water flooding or inclusion of formation water. It could mean anything depending on how it's been interpreted. Also, the image on the right, the one on the right, this one, you can see these are amplitude maps, one in 1985 and one in 1995, both showing you the effect of time-lapse seismic. You can see the yellow coloration on the ROMS amplitude map shows the area that is oil. That is for the 1985 ROMS map. And the blue part shows your water, and the green parts, green amplitude shows your non-reservoir rocks like your shales. Now you can see the area that is circled. You see the distribution of oil within the reservoir. This is a reservoir top. Within this reservoir top in 1985. Now by 1995, what happens is that the reservoir within this region, the oil has depleted within the reservoir. You can see that the yellow coloration which depletes or the yellow amplitude which depletes oil has reduced on the right part, on the right, on the image on the right. So in this area, the oil has depleted, but that is for the area that is circled in red. But on the other part that is not circled in red, the oil remains unchanged. You can see the oil amount, even the oil content has even increased on this part, on this part. So what is it showing you? It's showing you that the whatever oil well they have here is extracting oil in only this part of the reservoir. You are only extracting oil in this part of the reservoir. Okay, you're only extracting oil here. These other parts, there's nothing, the faults are not communicating. The reservoirs are not communicating. That means the fault is sealing. So it also helps to tell you whether your faults are sealing or your faults are not sealing, and whether you have sealing and non-sealing faults. So that is typically what your time-lapse seismic does, and a typical example of a typical 4D seismic. So the last one, but not the least, is your 4C. 4C seismic, the 4-component seismic size survey. What this one typically means, it's acquired like the OBC or the OBN. It's acquired at the ocean floor by OBN or OBC, okay? Mostly by OBC. What happens is that within the ocean bottom cable, you have four receivers within the ocean bottom cable lines. One, you have a hydrophone, and then you have a geophone as well. So you have 3 geophones within the receiver ocean bottom cable. One geophone will be measuring data in the vertical direction. Another will measure in the y direction, while another will measure in the x direction. What this means is that, you remember in our diagram of our geophone, I tried to describe or draw a geophone like this. It was shown like this, where you have the spike or the leg of the geophone, a spring, and a coil, a magnet, and a coil around the magnets. If you remember this image somewhere in this talk. Now, when the ground is vibrating vertically, in the vertical direction, this spring will dangle and dangle within the coil. The coil with the spring will dangle the coil around the magnet, and then electricity is generated. That is for vertical motion. So it's measuring the ground motion in the vertical direction. So the 4C seismic, you're not just measuring the motion of the ground in the vertical direction. You also measure the ground motion in the horizontal direction, both in the X direction and in the Y direction, okay? So your X and your Y, you measure the ground motion in X and Y direction. And then your vertical direction as well. So you have a motion monitoring sensor that is doing Z, X, and Y. And then you also have a hydrophone that also measures your S waves. You know, the S waves, sorry, that measures only your P waves, rather, not your S waves. That measures only your P waves, okay? While the geophones are measuring both your P waves and your S waves. So what's its importance? It utilizes where you want to suppress noise in areas that you have a lot of noise in your data, especially where the ocean water is very turbulent and you need to acquire seismic data within those areas. If you acquire with streamers, there will be a lot of noise in your seismic data. If you acquire with only OBN or OBC, there might also be a lot of noise because of the turbulence of the water body. So you need to do a 4C where you are measuring all the information that are measurable and ground motion in all directions. So if you do that, when processing, it becomes easier to suppress multiples that are usually associated with marine seismic acquisition and any other noise that may come in contact with your seismic through the ocean water movement and current and all that. So for your OBC, it gives you a better image of the subsurface compared to a conventional 3D seismic data, just as shown in here. So this part is your 3D and the lower part is your OBC. So if you look at the two data concurrently, you find out that the data on the image, the seismic data on the lower part has better data resolution. Event continuities are better because you used your 4C seismic to acquire that. So that is it for our seismic acquisition and seismic survey. So the next thing I'll point out before we call it a day in the next 2-3 minutes is your seismic survey deliverables. What are your seismic survey deliverables? In every seismic survey, there must be deliverable. One, the acquisition company will supply you with the seismic data in SEG-Y and SEG-D formats. Okay, so when we get to our processing, I will explain what SEG-Y and SEG-D means. I don't want to, there are differences actually. So they will acquire the data and record them in SEG-Y and SEG-D formats, and they will record them into tape cartridges. So I'll also show that in our next class. And they also record into hard disk, okay? They also record into disk. All of us know what hard disk is. And also, most of us may not have seen what tape cartridges. Tape cartridges are like floppy disk. If you met, I don't know if you people met floppy disk. Floppy disk that's used to measure only 100 megabytes of data. So that's what tape cartridges look like. But this one, they are magnetic tapes. And so they record more information than your floppy disk, and they are thicker than the floppy disk. Then you also have among the deliverables, you have your CDs. That's your compact disc, the normal CD that you know. And inside the CD, they will have the SPS files, your observer logs, your BlueStacks, your plots, and your maps in soft copy within the disk. Just your normal disk that you put in your laptops, if your laptops is disk enabled. Then you have your maps. They also give you your maps, your topographic map, your fold map, offset maps, etc. in hard copy. These maps will be given to you in hard copy. You also have your final acquisition report, both in hard and soft copy. What do you mean by acquisition report? You know the way you wrote your final year project in school. The way you wrote your project, after writing the project, you bind it, go to your supervisor will sign. That's the same way they will write a report. The way you wrote your final thesis in school, that's the way they will write a final report of the acquisition. Every information about the seismic acquisition will be contained in that report, and they will print it, they will bind it in hard copy, bind it the way you bind your school project, label it the way you label those. You know how they use golden color to label your school project? That is the same way they do it, and they will submit it to the company that owns the data, both in hard copy and in soft copy. These are the deliverables of your seismic data. So this is typically what your survey map and your topographic map will look like. If they just print it on paper, they can have it. You also have it in soft copy, your fold map and all that. This one is topographic map and all that. So The essence is just for you to know that after acquisition, the acquisition company will supply this information to the owners of the block or the company that owns the block where the acquisition was acquired. And so these are majorly the deliverables. So when I mean the seismic record here, what is recorded is the shot gather, what we call the shot gather. Okay, that's what is contained. We call them the shot gathers. So as they shoot the dynamite or the vibro or whatever, any shot they fire, they record it before they move and shoot the next one and record. So all those shots, we call them the shot gathers, and they record it into the tape cartridges and the hard disk, and then supply it to the owners of the block. So these are some of the references. I will send you the slides after now, or maybe by Monday. So here, this is where we call it a day for today. So I don't know if there's any question. We barely have time to answer the question. Our time is almost gone. So we call it a day from here. Moderator, thank you so much for your time.
Okay. Thank you, sir, for your time. Thank you very much. Thank you, everyone, for being here. Okay, sir. Will we be having another class tomorrow?
Tomorrow, no. I'm not too sure of Sunday evening. But if we don't do it on Sunday, we'll definitely have one within the week, maybe Monday before next Saturday. I'll communicate them with you if Sunday will be feasible. If we don't do this on Sunday, then maybe Monday we'll do that.
Okay, sir.
So we are done with seismic acquisition. I'll use the next class, I'll use it to give you an overview on processing, and then we'll head towards interpretation.
Okay, sir. Thank you for your
Okay.
Thank you for your time. Thank you for your valuable information that you are sharing with us. We are really grateful for what you're doing for us. So thank you. Have a good night's rest.
Okay. Thank you so much.
Yeah.
Good night, everyone.
All right. Good night, everyone. To all the mentees, thank you for coming. Good night. Let me end the recording now. All right.